Hello everyone, a very good evening to all. Myself Vivekananda Naik, I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. I welcome you all once again for this interaction session on the course Atomic and Molecular Physics. So till now we have completed all 12 interaction sessions covering the topics that has been taught in the course Atomic and Molecular Physics. So in the interaction session, we have briefly discussed the concept that was covered in that week's lecture, and then we solved a few sample problems. Uh, but today, since this is an extra session, so as I had told you yesterday, so we will do some sorts of revision. Like I will briefly cover all the concepts taught in this atomic and molecular physics course with course code NOC 26PH18. So let's start our discussion. So starting with the atomic physics. So initial week lectures was related to the model of atom. So if you talk about the atomic models, so a first model of atom was given by Thomson. So Thomson's atomic model was the first model of the atom given by Thomson, and according to him, so basically the model is also called as plum pudding model, where they where he said, like in a plum where the uh, protons are arranged in a negatively charged electron sphere, but there are some drawbacks like regarding to the stability of the atom, then some other things like, for example, when Rutherford's model came, so then to overcome the drawbacks, Rutherford's model came, and that was based on Rutherford's alpha particle scattering experiment, very famous experiment, where according to Rutherford, he said that most of the spaces in the atoms are empty, and almost all mass and all the positive charge of the atom is concentrated at the center, which is called as nucleus. So this is the nucleus of an atom, and the electrons are revolving around the nucleus in certain orbits. But Rutherford did not give explanation about the stability, about the structures of atom and all. Then came the Bohr's atomic model, where the concept of quantization of angular momentum and space. So quantization of angular momentum, it was based on the quantization of angular momentum, and it was given by 1913. So according to Bohr's atom model, we developed the Bohr's atom model for hydrogen atom. So it was based on the concept of L, which is MVR. It is NH cross or NH by 2 pi, and E is equals to NH nu. So these are the two quantization rules from which the model was evolved. And then we consider the model of hydrogen atom, where we found, suppose this is the nucleus, and in case of hydrogen it has only a single proton and single electron, and the proton is present here and the electron is revolving around the nucleus. Suppose the distance is r and the electron is present in n cell. So that will be the velocity, expression for velocity, expression for radius, expression of energy of the hydrogen atom that we calculated. So it was, so V, the velocity of the electron was Jd square by 2 epsilon 0 nh, and radius of the orbit was h square epsilon 0 by pi mjd square, and then the energy of the electron in nth orbit, it was m e fourth z square divided by n square h square epsilon 0 square. Now from this we calculated the energy as minus 13.6 electron volt 1 by n square. So depending upon the value of energy, we found that the energy levels are not equally spaced. So this is E1, this is minus 13.6, then it will be minus 13.6 by 4, then minus 13.6 by 9. So the energy gaps are not equal. Then that also gave rise to the spectra of hydrogen atom. So hydrogen atom spectra, we found out the wave function, the wavelength, frequency, and wave number of the spectra, and the formula was 1 by lambda equals to r 1 by n1 square minus 1 by n2 square, where r was Rydberg's constant, where r was Rydberg's constant, and what is the value of the Rydberg's constant? It is 1.097 into 10 to the power 7 meter inverse. Then depending upon the expression for Rydberg's constant, like in case of so if you talk about the Rydberg's constant, so its value is m e fourth divided by 8 epsilon 0 square c h cube. But here if you see m is me, that is mass of electron was considered. But when we are considering a system of one proton and one electron, the mass of electron can be taken only in the case when the nucleus is at rest. But when the nucleus is also moving, so we need to consider the reduced mass of the atom. So for that case, this m will be replaced by mu, and from this mu we so this is called as r infinity. Then RH we can say, where we can, so there will be different value for hydrogen, different value for deuterium and tritium, and corresponding to which we solve different types of numerical problems also. Now if you talk about the spectra of hydrogen atom, so suppose this is n equals to 1, then this is n equals to 2, gap will be decreasing with n, so n equal to 3, n equal to 4, n equal to 5, like that. So it is, so when the transition occurs from higher or higher energy levels to 1, it is called as Lyman series. Then from higher orbits to 2, it is called as Balmer. Then this is called as Paschen. Then this is bracket. Then for n equal to 5, it is Pifford series. And also in case of Balmer series, we have H alpha, H beta, H gamma, H delta, like that. So they corresponds to visible spectrum. Lyman series corresponds to UV region, and Paschen series, bracket series, they corresponds to infrared and all. So with increase in, so as you can see, the difference in energy is more, so the wavelength is less. So the wavelength of Lyman series is less than the wavelength of Balmer series, it is less than the wavelength of Paschen series, like that. Similarly, if you talk about the frequency of Lyman series will be maximum. The frequency, so this will be the relationship between the frequency and all. So also we solved with the first member, the last member, the problems related to that we also solved. Then after the there was drawbacks of Bohr's atomic model also. Drawbacks of Bohr's model, then which again was given by Sommerfeld's, and it's called as Sommerfeld's atomic model, where there was another quantization was introduced. So the levels which was originally given by Bohr as circular, then it was not circular, it was elliptical, and it was elliptical in shape, and circular is the case. So we there was another quantum number. So in case of Bohr, we had a single quantum number n, but we there was introduction of another quantum number in Sommerfeld. So we had n by k. So we found that b by a is equals to k by n, and when n equals to k, then it is a circle, but k will be less than equals to n. So in that case, corresponding to each label, we got different sub labels also. Then after that, there was the concept of vector atom model. So from vector atom model, what we studied. So so in case of vector atom model, so the we so new quantum numbers are introduced: angular momentum quantum number. So we got new quantum numbers n, then l, then ml, and ms. So this is principal, this is azimuthal, this is orbital magnetic quantum number, then this is spin magnetic quantum number. Also we found the concept of, also we discussed also the concept of gyromagnetic ratio were discussed. Concept of gyromagnetic ratio, so which was mu l divided by l. So this was minus e by 2m. Sorry, so if you say mu l by l, it will be minus e by 2m, or we can say mu l vector is equals to minus e by 2m l vector. So that was due to the charge of electron. So so then also we got another spin magnetic moment. It was minus e by 2m s vector in and gs, where gl was 1 but gs was 2. So corresponding to that, we had different orbitals, like for s l was 0, for p l was 1, like that. Also in quantum mechanical, if we write l vector as l into l plus 1 root over h cross, and lz vector is mlh cross. This is the component of angular momentum along the magnetic field. Similarly, we got s vector is s into s plus 1 root over h cross, and ms h cross is sz mod. So also the concept of space quantization was discussed. Space quantization. So space quantization basically says the orientation of angular momentum is also quantized. So corresponding to 1L, we have different ml values, and the orientation depends upon that ml value. So when L equal to 1, there are 2L plus 1 values of ml, that is 3. When L equal to 2, ml has 5 values like -2, -1, 0, 1 and 2, 5 values. So there will be 5 different orientations of the orbital. Also, the concept of uh, um, Larmor precision was also discussed. So the frequency of what's the EB by 4 pi m. Again, the concept of Stern-Gerlach experiment were discussed. Stern-Gerlach experiment. Basically, it led to the discovery of electron spin, discovery of electron spin, and it also explained the concept of space quantization. Then also we found Bohr magneton. Bohr magneton, the value of the Bohr magneton is 9.27 into 10 to the power minus 27 joule per Tesla, and this is the unit of atomic magnetic dipole moment. Atomic. Also, in case of nucleus, we have nuclear magneton. So this is EH cross by 2me. This is EH cross by 2mp. This is called as nuclear Bohr magneton. So when the concept of L and S came into picture, then according to the vector model, total angular momentum is also given by J vector, where J vector was L vector plus S vector. From there, the concept of multi-electron atom is discussed. Multi-electron atom. So in case of multi-electron atom, we discussed about LS and JJ coupling, LS and JJ coupling. So what is LS coupling? So LS coupling occurs in case of lighter atoms. So in case of lighter atoms, there are lesser number of electrons. So the uh, interaction between each electrons that dominates over the spin orbit coupling. That's why suppose there are number of different electrons L1, L2. Suppose there are two electrons having orbital quantum number L1, L2 and spin quantum number S1, S2. So L1, L2 it gives rise to capital L, then S1, S2 it gives rise to capital S, and then this is called as the concept of LS coupling, and then the energy level gets splitted. So if we discuss that, so what we can say, so for example, then this L plus S they give rise to J. So let's consider the concept of LS coupling. Suppose there was two electrons, suppose two p electrons. So p means L1 is 1, L2 is 1. So L will be 0, 1, 2, and S1 will be half, S2 will be half. So S will be 0 and 1. So when L equals to 0, S equals to 0, J is 0. When S equals to 0, L equals to 1, J is 1. When S equals to 0, L equals to 2, J is 2. But when L equal to 0, S equals to 1, then J is 1. When L equal to 1, S equals to 1, J is 0, 1, 2. When L equal to 2, S equals to 1, J is 1, 2, 3. Also, the labels are represented in terms of their spectroscopy notation, which is written as 2s plus 1 Lj. So if you write it, so S0 means 2s plus 1 is 1, so it is 1s0, 1p1, 1d2. Here also S is 1, so this is 3s1. Here again this will be 3p012, this will be 3d 1 2 3. So this is the way in which the splitting of the spectral line occurs, and we get the fine structure splitting of the spectra. So that was the concept of LS coupling. Now if we talk about the concept of JJ coupling, so in JJ coupling what happens? So L1 plus S1 they give rise to J1, L2 plus S2 they give rise to J2, and it occurs in case of heavy atoms. So in case of heavy atoms, it has more electrons. Sorry, in case of heavy atoms, it has more electrons. So the spin orbit coupling dominates over the residual coupling. So how we represent in case of JJ coupling? So suppose, so take the example. Suppose L1 is 1, L2 is 2, S1 is half, S2 is half. So here J1 will be half 3 by 2, J2 will be 3 by 2, 5 by 2. So how we can write it? So it will be half, we can write it half 3 by 2, 3 by 2, 3 by 2, then 3 by 2, 5 by 2, and half 5 by 2. Also if you see, this will give you another j value, so this will be 3 by, so this will give total j, it will be 1 2, it will be 0 1 2 3, it will be 1 2 3 4, and it will give 2 and 3. So after the concept of multi-electron like LS and JJ coupling, the spectra of alkali metals was also discussed, and then we discussed about the concept of uh, G-man and Stark effect. So G-man effect is the splitting of spectral lines in presence of external magnetic field. So in case of G-man effect, there is also two different G-man effects. One was normal G-man effect, where a single spectral line gets split into three components, and there was another which is called as anomalous G-man effect, where it splits into more than three lines. So in case of normal G-man effect, spin is 0, but here it is non-zero. So if you discuss about normal G-man effect, So in case of normal Zeeman effect, so S is 0, so we have only L. So the label gets splitted in terms of their ml values. So the uh, selection rule is delta ml is equal to 0 plus minus 1. So delta ml 0 corresponds to one line, plus 1 corresponds to one line, and minus 1 corresponds to one line. So there are three components. That is normal Zeeman effect. Then there was the concept of anomalous Zeeman effect. Because of anomalous Zeeman effect, S is not equal to 0. So J has more significance. So according to MJ values, we have the energy levels get split. So selection rule is again 0 plus minus delta mj is equal to 0 plus minus 1, and 0 to 0 transition is not allowed. So also depending upon the transition, we have multiple components. Also there is another concept. So in case of strong magnetic field, what happens, the splitting, the coupling between the L. So here L and S, they were getting coupled to give J value, and the significance of Mj was the value Mj has significance. Mj had significance, but in case of Pastenberg effect, what happens? In case of Pastenberg effect, when the magnetic field is too strong, then the coupling between pin and electron is broken, and they are arranged in terms of their ml and ms value. So in case of Pastenberg effect, both ml and ms have significance. So we also solved a few problems based on those concepts. Also there was another concept related to Landé G factor. So the value of Landé G factor was Gj was 1 plus j into j plus 1 minus, sorry, plus s into s plus 1 minus l into l plus 1 divided by 2 j into j plus 1. Also we solved a few problems related to Landé G factor. So if a label is given, suppose 2s plus 1 lj, we know, then we can find s, we can find l, we can find j, and then we can calculate the value of Landé G factor for a particular label. Basically what is how the expression came. So the Landé G factor came from the expression, like in case of so mu l vector, we are writing e by 2m gll vector. In case of mu s vector, it was minus e by 2m gss vector. Similarly, if we write for j vector, it will be mu j vector minus e by 2m gj j vector. So gj is basically the contribution of l along j and the contribution of s along j. So if we calculate, we can get the expression for Landé G factor. So we discussed about normal Zeeman effect. Then the anomalous Zeeman effect we also discussed. So one of the example of anomalous Zeeman effect was D1 D2 line. So one was 2p half 2p3 by 2, 2p half 2p3 by 2. So in case of D1, the transition occurs from 2p half to 2s half, and D2 is 2p3 by 2 to 2s half. So if you arrange, so this was 2p half, and the transition was to 2s half. But in presence of magnetic field, it gets splitted into different labels. So as we had already discussed, so here it will be having the ml values. They have, sorry, since 2p means 2s plus 1 is 2, so s is half. So s is not equal to 0, so it is the concept of anomalous Zeeman effect. So in case of anomalous Zeeman effect, we know the labels get splitted in terms of their mj value. So since mj is half, it will be splitted into two values, sorry, into two labels. One is minus half, another is plus half. So it was minus half plus half. Similarly, this 2s half, it also gets splitted into minus half and plus half. And if you talk about the transitions, possible transitions, so minus half to minus half is allowed, plus half to minus half is allowed, then minus half to plus half is allowed, and plus half to plus half is allowed. So there are four lines. So this D1 line gets split into four components in presence of the magnetic field. Similarly, if you talk about D2, it was 2p 3 by 2 to 2s half. So 2p 3 by 2 means it will get split into four labels. So this was minus 3 by 2 minus half, half 3 by 2, and it gets split into two labels, minus half and half. So minus 3 by 2 to minus half, then there will be these two, then these two, and then 3 by 2 to half. So 6 lines. And the selection rule is again delta mj is equals to 0 plus minus 1, and uh, 0 to 0 was not allowed. So this is the way in which the D2 line gets split into 6. So D1 line gets split into 4 components, and D2 line gets split into 6 components in presence of magnetic field. Then also the quantum mechanical treatment of hydrogen atom I discussed. Quantum mechanical treatment of hydrogen atom was also discussed. So I'll be back in a few minutes. So if you talk about the quantum mechanical treatment, the basics of quantum mechanics was discussed. Basics of quantum mechanics was discussed. So in case of quantum mechanics, it was all represented by wave number, and the physical quantities are represented in terms of operators. And then the sorry again we solved Schrödinger's wave equation, which was h psi equals to E psi, where h was p square by 2m plus Vx, where is the Hamiltonian operator. And we solve the Schrödinger wave equation. So in case of uh, uh, hydrogen atom, so it has a proton, and the electron is able beyond the nucleus, and the force and the potential is a function of r, which is minus E by 4 pi epsilon 0 r. And if you see r, if you convert it from Cartesian coordinates, it will be x square plus y square plus z square root over. So then we solve the Schrödinger equation. So it was psi r theta phi independently, because it will be difficult to solve in Cartesian coordinates. So then again we got the wave function solutions as psi nlm. So where it is r nl equal to y theta phi ln. This is called as spherical harmonics also. And then the few concepts related to the outcomes of the outcomes of the solution, that is the solution of the Schrödinger equation, are discussed, which gave rise to the concept like phi the nucleus, phi the electron can be present inside the nucleus. Then the probability density distribution is also calculated, and we also the expectation value formula, like in case of classical mechanics we can measure a physical quantity with certainty, but in case of quantum mechanics, since particles show the wave nature also, so we found the expectation value. So expectation value or average value, suppose we want to find the expectation value of a, then it will be written as minus infinity to plus infinity psi star a cap psi dx divided by psi star psi dx, is called as average value or expectation value. Then after that we discussed about the concept of molecular spectra. So if we discuss about the concept of molecular spectra, so so molecular spectra, we have electronic spectra, then rotational spectra, and vibrational spectra. And also the So if you talk about rotational vibrational spectra, so electronic spectra, it has the energy of the order of eV. In case of rotational spectra, it has the energy of the order of 10 to the power minus 3 eV, and in case of vibrational spectra, it has order of 10 to the power minus 1 eV, or few tens of eV is electronic spectra. So electronic spectra is visible or UV region. So electronic spectra is invisible or UV. Rotational spectra corresponds to microwave. Section of the electromagnetic spectrum, and vibrational spectra corresponds to infrared. So the molecule that show rotational spectra, they are called as microwave active, and the molecule that show vibrational spectra, they are called as infrared active. So if you talk about the label, so suppose this is ground state, and this is the excited state. Suppose this is A and this is B. So when the transition occurs from A to B, this is electronic spectra, and corresponding to each electronic label, we have a number of vibration level. This is V equals to 0, V equals to 1, V equals to 2. So the transition occurs from one level to another level. This is called as vibrational spectra, and corresponding to each vibration level, we have rotational levels given by rotational contour number J is equal to 0, 1, 2, 3, like that. So when the transition occurs from one rotational level to another rotational level correspond to same vibration level, we call it as pure rotational spectra. And when the transition occurs from one rotational level to another rotational level of different vibrational state, it is called as row vibrational spectra. And if you talk about the molecules, we have diatomic molecules, so we have homonuclear molecules and heteronuclear molecules. If you talk about heteronuclear molecules, they have permanent dipole moment, so they show rotational and vibrational spectra. But in case of uh, homonuclear molecules, they does not have permanent dipole moment, so they are not show rotational spectra. They only show electronic and they also electronic spectra. So now also the concept of rotational spectra were discussed. So rotational spectra. So the concept of rigid rotator was first discussed. Rigid rotator. So in case of rigid rotator, the so the rotational labels as is represented by the rotational quantum number. So this is rotational quantum number, and the energy of the rotational label is given by E equals to J into J plus 1 h cross square by 2 mu r square, where J is 0, 1, 2, like that. There we introduced a rotational constant B, which was h by 8 pi square IC, where I is the moment of inertia, called as mu r square, or mu is the reduced mass of the system, and mu is m1 m2 divided by m1 plus m2. That is the reduced mass of the system. And if you talk about the uh, energy in terms of wave number, it is given by Ej equals to B J into J plus 1, where B is called as the rotational constant. So this is called as the rotational constant. And depending upon the value of J, so E0 will be 0, E1 will be 2B, E2 will be 6b, E3 will be 12b, E4 will be 20b, like that. So if you talk about the labels are also unequally spaced, because first this is 0, then 2b, then it is 6b, then this is 12b, this is 0, 2b, 6b, 12b. So if you have the transition, so this is 0 to 2b, so it is 2b, then 2b to 6b, it is 4b, then 6b to 12b, it is 6b. So the separation between the two lines are 2b and they are equally spaced. Remember, this is in wave number unit. And also we discussed about the concept of the number of atoms in jth state. So nj will be n0 to j plus 1 is the weight factor, then it will be exponential minus ej minus e0 divided by 80. Also the concept of non-rigid rotator was discussed. In case of non-rigid rotator, the term in the terms energy term in terms of wave number is given by b j into j plus 1 minus d j square into j plus 1 square. So if you see, so in case of rigid rotator, if this was the level, so this minus sign is given, so the level gets splitted in, so the energy is lowered in case of non-rigid rotator for each level, and due to that also the spectra that are used to be equally spaced, no longer they are no longer equally spaced in the rotational spectrum. Now again the concept of vibrational spectra were discussed. The concept of vibrational spectra. So if you talk about the potential energy of a simple harmonic oscillator, it was given by Vx. It was Vx at x equal to x0. If you do the Taylor expansion, it will be Vx0 plus del V by del x at x equal to x0 plus 1 by 2 factorial del square V by del x square at x equal to x0, like that. When Vx equals to 0 and del V by del x is 0, the next term is del square V by del x square. So we write it as Vx is equals to kx square, half kx square, where k is del square V by del x square at x equals to x0. So in case of harmonic oscillator, the energy level is given by V plus half Sc omega E, but in case of anharmonic oscillator, the levels are given by Ev equals to B plus half Hc omega E minus B plus half square Hc omega E Xc, where omega E Xc is called as anharmonicity and Xc is called as anharmonicity constant. So again the selection rule delta V is equals to plus minus 1. So here you see the energy levels are equally spaced. So because this was half, 3 by 2, 5 by 2, like that. So there is a single spectra. So this is Again Hc omega e, this is Hc omega e, so we get a single spectra corresponding to the transitions. Also we solved a problems related to the concept of anharmonicity, and then we also discussed about in the last interaction session, that was yesterday, we discussed about Raman spectra. So Raman spectra is basically when a light of atom wavelength, for example, through laser, it is incident on a molecule. Then some of the photon gets absorbed by the molecule, and most of the photon that get reflected, they get scattered without any change in energy, which is called as relay scattering. So Raman spectra and is relay scattering. Then there are Stokes line and anti-Stokes line. Stokes line and anti-Stokes line. So this was relay line, then this was Stokes anti-Stokes line, and this was Stokes line. So this is Stokes, this is relay, and this is anti-Stokes. So if we talk about the pure rotational Raman spectra, we found that this is 0. So the first member of the anti-Stokes or Stokes line, they are 6b shifted by 6b, but due to the selection rule delta j is equals to plus minus 2, the distance between the two lines is 4b. So here also 4b, then here also 4b. Also there are concepts related to classical concept and quantum mechanical concept are discussed. So in case of Stokes line, the energy get transferred from photon to the molecule. So the frequency of the scattered light is less than the frequency of the original light. But in case of anti-Stokes, energy gets transferred from molecules to photons, so the frequency is more than the incident frequency. And if we talk about the intensity, Stokes line has so relay line has maximum intensity. Then in between Stokes and anti-Stokes line, Stokes line has more intensity than anti-Stokes line. And also we solved a number of sample problems related to the concept. So in this way, we covered all the topics that was taught in this atomic and molecular physics course, and also we have solved a few problems that will definitely help you in solving your course assignments. So I hope the concepts I covered briefly will provide you with a with some sort of revision for your exam if you are appearing. So that's it from my side. I hope we will meet in some other courses in future, some other NPTEL courses in the future. Till then, that's it from my side. Thank you all. I would like to thank you all for joining in this course and for attending this interaction sessions. And I will like to wish you all the best for your exams of this course and for other courses also if you are registering. Thank you.